Okay, I'm going to start with Chapter 4, Force System Resultants. Okay. Thus far, the way we've handled force systems is we've basically assumed that all the forces were acting at a single point or particle. Now we have to consider that forces don't act, and in the real world, most cases, forces don't act all act at the same point. So we have another thing to be concerned with, and that other consideration is a moment. Okay. Which basically is a force acting at a distance from a point or a line. Okay. So here's an example. Okay. You have beams used to bridge gaps, right? Or a bridge gap in a wall. In a situation like this, let's say we wanted to know how much of the force is acting down at point A and at point B. Okay. Well, we could do the summation of the forces in the y direction, and what we would have is this is F, and if this thing has some weight associated with it, it has an F, and that's pushing straight down, and then we have a component, we have some other force, a reaction essentially at this point that's pushing back up at this point on the beam, and we have another force over here. Now, if we assume like the beam has negligible weight compared to this force, we can kind of neglect it, right? And for this simple example, we'll think about it that way. So you have some force acting up here and some force acting up here, and those are considered to be the reactions. Now, if we're thinking about this just in a summation of forces, we would end up having two variables, a reaction here and a reaction acting up here. So we would have one equation and essentially two unknowns. Okay. Well, the second part of this equation, we have to think about it in terms of moments. Okay. Now, a moment about a point is basically defined as a force times a distance. Okay. So, and the force that you have to be concerned with is acting at 90 degrees at a 90-degree angle, or perpendicular to the line or the beam or the connecting point that we're interested in looking at. Okay. So like in this case, it's acting straight down. So we would measure a distance from basically from A all the way over to here to F. And the moment due to this force pushing down here is just the distance from here to here. And we're looking at, the two-dimensional case right now. And the force that's acting at 90 degrees, okay, with that length of the beam. All right, so that would give us just F, this F times dA, which is from here to here, okay? Now, that would give us a number. Now, this thing is in equilibrium, or we assume it's in equilibrium. We would have to have the summation of all the forces equal to 0. So whatever rotation about point A this force would cause, acting at this distance, has to be counteracted by something else. And what ends up happening is that we have another force acting from here straight up, and we have a distance from A to B. So we have another moment, or reactive moment, or reacting to that. So we have another moment due to the force acting at this point at point B to stop essentially from this rotating. So the way we define it is that if it causes a rotation about a point in the positive, in the clockwise direction, it's considered to be negative. And if it's a force, we would have a force acting up here, and that would cause rotation about A in the counterclockwise direction, like around like this. That would be considered to be positive. So if we added this F times dA times whatever force is acting here, we'll call that FB, let's say, times this distance from A to B, and we took those two and added them together, we should come up with 0. So what ends up happening in this case is that we have an equation that we created from the forces, and we're going to look at, we'll look at more examples if you got the general idea right now. We have an equation due to the forces, and we also have another equation due to the moments. And we could do a moment equation about A, or we could do it about B if we wanted to. But basically, we have two equations and two unknowns. And the two unknowns were the reactive force pushing up here and the reactive force over here. So with that, we can actually solve for the reactive force pushing up at this point and the reactive force pushing up at that point. Okay. And that's kind of for the two-dimensional problems what we're going to be looking at. Okay. Okay, here's another application. And this one is a hammer. Let's see, what sort of action does force FH at handle pull the nail? So if you think about it, like maybe this is our point here, and if you drew a line like straight up and meets here, you could create a moment, you know, this force times this distance from here to here, from point O all the way up to that, acting at 90 degrees. That will give you some rotation, like about point O in the clockwise direction. And then you would have other rotation about point O due to this F of N acting in the other direction, okay? Which would basically be like, you know, distance from this point straight across where it meets this at 90 degrees, okay? Now, you know, if you know what this is, but whatever this force is, and assuming that you haven't pulled the nail out, so this has a reactive force basically in the other direction, you could actually go through and figure this out, right? So if you know what FH is here, you could come up with an equation, and you also have a reactive force here, right? So you have FH, and let's say, let's see, what sort of action? Okay, so if you know what this one is, but let's say you don't know what this one is, and you don't know what this is necessarily. All you know is it's not pulling it out. So you have two unknowns, right? So you'd have to create a moment equation like before about this point O, and also do a summation of the forces like in the X. And in this case, there's only, I'm sorry, in the Y direction, because there's only reactive force in the Y direction here. So as before, you would have to do the same as we did in the previous example. You'd have to come up with two equations, all right, for that. And then you can solve for this F of H here, okay, acting upward. And you could also solve for what this is too. All right. So it gets to be a little bit more involved, but this is like the next step. Okay. So as I was showing when we were talking about those examples here, you can really think about it in terms of like a wrench, right? So you have a wrench, you have a wrench connected to a bolt, and you push on the wrench, it causes this bolt to rotate and either, you know, turn in or turn out. And how do we figure out what that moment is acting about this bolt? Is basically the distance times the force that's acting at a 90-degree angle here, okay? If it wasn't at 90 degrees, of course, you'd have to break it up into two components. A component that's 90 degrees to this, or perpendicular to this line of the wrench, the center line of the wrench. And when she did that, it would be that perpendicular component times that distance. Okay, so it's also called the torque. Okay, all right. So the thing we need to pay attention to, and here's like a top view, and this is so-called sense of rotation. Okay, if it causes rotation about that point, so you have a force acting at some distance here, and it causes counterclockwise rotation, it's going to be positive. Okay. If it's when you create your equation, so this would be F times D, if it caused rotation the other direction, it would be negative F times D essentially. Okay, so like if this force was reversed. So we have to pay attention to this sense, all right, when we're talking two-dimensional cases. When we get three-dimensional cases, it actually works out in the equation like what the appropriate components and the magnitude of the components and the signs, whether or not there are the senses of those components, will work out in the equation, okay? But when we're dealing with two dimensions, we have to pay attention to this. Positive, if it's causing counterclockwise rotation. Negative, if it caused clockwise rotation, okay? All right, continuing on. All right, so here's a special case that, you know, you have, let's say, in this case, you have a bar here, and it's connecting from, you know, at point O, and we're trying to find that rotation about point O, and the bar goes up like this and goes up like this at 90 degrees. And then you have a force acting at a distance here, okay, off at an angle. Now, you have some choices here. You could actually figure out, oh, okay, I have this force. It's acting at, you take this line of force and just draw it straight on through, draw a straight line all the way through. And if you can come up with the length, which you could, and it might be easier to do this a little bit differently, but let's say you come up with the length of this distance here, it would be just this distance times the magnitude of this force, okay? That may take a little bit to figure out how far this distance is, although you could do it. The other way, which is typically easier, is to think about taking this force, break it up into its x and y components, and then drawing the line straight on through here, straight line through, and then finding the distance where it crosses at 90 degrees, where this bar, this line meets at 90 degrees. So you would find the length of this from here to here, and let's say that's a length of b. So it would just be here to here times f of x. Will give you the rotation due to the x component. And then if you go from here all the way over to where this meets, which will be length a, okay, if we went straight down, straight across here and had this line straight down, and that would be the moment due to the y component of the force, okay? Now, here's the overall moment from this force. So you have f of y times a minus f of x times b. And the reason it is, the first one's positive, of course, because it would cause counterclockwise rotation about the origin, or about O. And then it's negative here because it would cause, this force would cause this to try to rotate in the clockwise fashion, okay? All right. The next thing is cross product. So that's like the overview of 2D. We have a bunch of examples that we'll take a look at as we go along when we get into the third section. All right, the next thing to introduce is the cross product, okay? Vector cross product. All right, so for 2D cases, just like the examples I showed you, work very well. The problem comes into play, not that it's a problem, but the problem gets a bit more complicated when you're handling three-dimensional when you're handling it in 3 dimensions, okay? And we could break up the problem to a bunch of 2D problems and solve it that way, but generally it's easier to use the vector cross product to actually solve a problem so that you can come up with a moment. And one of the things you're going to find about a moment itself is a vector, okay? Now, when we did this, the previous examples I showed you here, came out moment was a scalar, okay? And, and what does it tell you at the end? Essentially, it says, oh, okay, I have a moment about this point, and, positive or negative, whatever this comes out to be, depending upon the angles here. This would tell you about the overall moment or rotation about this point, okay? And if it's negative, it says, oh, it's trying to rotate in the clockwise fashion. If it came out to be positive, I know it's trying to rotate in the counterclockwise fashion, all right? But when it's in 3 dimensions, it gets to be a little bit more involved. And in fact, if you think about it, this is 2 dimensions, but then there's a 3rd dimension that's coming either, going right into the screen or coming straight out. That would be like the Y, not the Y, the Z dimension, okay? So that's what we're getting to. So we want to have a technique to handle 3-dimensional forces, all right? 3-dimensional moments, 3-dimensional forces. Okay. So the cross product by definition is this, essentially, or the vector cross product, okay? Essentially what it is that you're taking, you can use the right hand, follows the right hand rule. It's like point your fingers off in the direction of A. Let's say you're doing a cross product of 2 vectors. So your fingers go off in the direction of A, okay? And this is your right hand. And that is your first vector, okay? The second one, your fingers curl, and they curl in it, that they sort of create an angle between the two, between that and the next vector, B, okay? So from relative position, right? It's like it curl off in the direction. So if B was over here, it would be entirely different. It would be a result that would actually have a opposite sort of all the components would have opposite signs compared to what we would have if it's over here, okay? So it's first vector, and then the second vector, you curl your fingers in the second vector for the angle that is between the two. And you curl your fingers, and that gives you the next one over here, okay? Provided that it's over here, right? Like I said, if it's over on the other side, then it would be, you'd have the right hand rule, but your thumb would actually be pointing downward, okay? But you curl them off in the direction of the next vector. So the next thing you have is your thumb. The thumb will point in the direction of the vector made by the cross product of these two vectors, okay? So that's like the end result. That's like your moment vector, okay? So here is how we can write this, all right? The magnitude and direction of the resultant vector is this. Okay, so cross product just by definition is this, all right? So it is a vector, and the vector is in the direction of C, right? This is U of C. U of C is telling us that the direction is essentially, gives us the unit vector for that other vector. So like when we did cross product in, let's say A and B were along the X and Y plane, we would come up with a vector that's perpendicular to it, that's acting either, positive Z direction or negative D direction, depending upon, following the right hand rule. Okay, so by definition, it's just A cross B, which basically means the magnitudes times together, times the sine of the angle between those two. Okay, so it's another approach you could actually get the angle between the two. And then the direction, as you see. Kind of like the dot product, except dot product gave you a scalar. Now cross product is going to give us a vector, all right? And how it's calculated is a little bit different. All right. Okay. Okay. So here we are looking at it in our case when we're dealing with our, vectors, let's say, essentially in the X, Y, and Z, right? So if you have a vector that's off here, another one that's off here, then the Z vector is just going to be perpendicular to that, okay? All right. So one of the things we need to think about when we do a cross product, and just to think about it, like if you have the unit vectors, right? I and J, and you cross them, and this is going to be important as we go through and perform the operations. You'll see that how it comes out is due to that, the nature of these two being, I and J crossed together like that equal to K, all right? So what it essentially says is, you have two vectors, and this is going to give you one that's perpendicular to the other two, okay? But we'll need this in terms of unit vectors also. Now, if you had two vectors that were right on top of each other, let's say they're both were I, they're parallel to each other, so this is I, and you cross them together, that's going to give you 0. And if you think about it, if you go back up, just to take a look at the definition, that the sine, if you had 0 degrees between the two, of course, it's going to come out to be 0. All right? Okay. Continuing on. Okay. So you can write this as a determinant. All right? So you take your two vectors, your A and B, and typically when we do it, where you're going to use it with it's going to be R cross F, or our vector that represents like our position, crossed with our force vector, right? But if you had in general, you had your two vectors, you'd write them like this. You just say I, J, and K, then you'd put your A vector, whatever's one to the left first, and then the second one, B, would be just below it. Okay, so you write it like this. All right. Now, you can do this with two-dimensional determinants. There's other ways where you can do like column extension, which I like to do sometimes, and write it like that to solve these. But the basic idea is this, right? So if you're doing element I, right? So let's say I'm trying to calculate the I component of the cross product, right? Because this is going to give me a vector, this thing, right? You just basically cross out, the top row and the first column, the I column, and then it's just going to be, you do this, AY times BZ minus AZ times BY, okay? And then the J one, so you're basically taking a 3 by 3 and creating a 2 by 2. And then the next one, when you're trying to figure out the j, you remove the j, okay? And then you do a times bz, see that, right? And it's a negative here, okay? And then it's minus a bx times az, okay? And then the last one, just make sure you remember the sign. And then the last one is, you remove the k, and then you do ax times by minus ay times bx, okay? So this falls in the category of linear algebra, but, even if you haven't had it yet, to go through and calculate the components of the cross product, this is it, really. That's all we have. We have three dimensional space that we're working in. So our matrices are going to be just like this. They're going to be written 3 by 3. All right. And that's pretty much it for first two sections. And I'll talk about this one a little later. All right.